Okay, well, welcome everybody to another one of our TESS seminars. TESS, of course, is our Center for Tropical, Environmental, and Sustainability Science. It's primarily a terrestrial group at JCU, and in fact, this is relatively unusual to have someone like Josh Cinner, but I wanted to take the opportunity to get Josh because he's doing so many interesting things right now. Until recently, Josh was at JCU, and then he won an Australian Laureate Fellowship, which is just about as high as the scientific awards go. And he became very popular. There were a lot of people that wanted him. He received other offers and ultimately decided to take one at the University of Sydney. And he was just, if you were here a minute ago, you were hearing Josh lamenting a bit the housing situation in the Sydney area, which of course he knew going in. Josh he's from the US originally. He got his master's at the University of Rhode Island and then his PhD here at JCU. He's primarily a social scientist, and he has worked all over the world. I mean, I had a look at his brief bio, and my goodness me, there's a whole slew of different countries in just about every continent, I suppose, except for Antarctica. And so I'll go ahead and turn things over here soon to Josh. Josh, I want to let you know we also have a substantial number of people following online. Currently at 16, but it'll continue to increase. So we have our people trained to start a little bit late, which is probably what's happening here. But anyway, without further ado, we'll hear from Josh Cinner and his very interesting initiatives that he's setting up right now to look at the health of the world's oceans. Thank you, Josh.
Thanks, Bill.
Oh, sorry, I forgot to mention that we recently published a paper in Nature. Not that I'm name dropping or anything. Yeah, with Josh.
I'll drop that in here too, don't worry. So I wanted to do something a little bit kind of different to start. And one of the amazing things about humans is our cognitive ability to kind of make connections between things. That sometimes doesn't serve us that well, because sometimes when we learn something, our brain makes these connections and we think, well, that was obvious. I kind of knew that all along, but we didn't. So what I thought I'd do is we'd actually do a little poll and find out kind of what you guys think before, and then I'll tell you the answer later. So I want your guys' opinion, and for those of you just joining us, there's a QR code here, or you can go to menti.com. This is where I'm actually telling you to take out your devices in the middle of a talk. You can go and do that now. You can log on and use the code. And I want you guys to use your best guess on what proportion of fish in the ocean is attributable to management or conservation. And what I mean by that is compared to a counterfactual if there was no management at all and people just could fish as much as they wanted everywhere. So what proportion of fish in the sea do you think is attributable to management or conservation? Now, the answer that I'm going to give you guys a little bit later, I'm going to give you guys in kilograms per hectare, basically. That's the amount of fish per unit area. And I'm going to do it for coral reefs, for coral reef fish. But I think the answers are probably transferable. Now, I will just say, if you guys are feeling like, oh, I'm a terrestrial group, I don't really know, or I don't work on fisheries or conservation, I will promise you that you are actually no less informed than the world's expert on this topic, because we actually have no idea what conservation is actually achieved. And I'll get into that a little bit more later, but we're using a lot of the wrong metrics to find out. So I'll come back to this poll at the end, but we've kind of got the spectrum from probably about 10% up to 100%. So that's pretty cool. I'm going to switch over to the talk, and then at the end, we'll kind of come back to this. Yeah. So as Bill mentioned, I'm a social scientist. I'm a geographer by training. I study human environment interactions from local to global scales. I focus primarily on coral reefs. I think reefs are an incredibly interesting system to study. They respond to, I mean, they're beautiful in their own right, and they're just amazing, and I fell in love with them. They're a good system to study because they kind of respond to human impacts and management and timeframes that actually make studying them reasonable. You can see effects of management in a couple of years. You can see human impacts almost immediately on them. So they're kind of a convenient system. And quite frankly, I work a lot with fishermen, and they are just the craziest people on earth. They are like the antithesis of an economist's rational actor. They often act in really really they're predictably unpredictable. And so they behave a lot more like a gambler or a gold miner in that they're going for a windfall, right? They're going for a huge catch rather than the kind of high average catch, which may be more profitable. There's a lot of prestige and things that they're following. So they make all these decisions that are kind of counter to what economic theory would predict. And so that's really interesting to study as well. Now, I got my start working in coral reefs back in the mid-90s when my ponytail and I signed up for the Peace Corps. And I got stationed in Montego Bay, Jamaica, and I got stationed in a marine protected area, actually. I was the education coordinator for a coral reef marine park there. And that's when I realized how important studying the human dimensions of conservation really is. There was a lot of conflicts with the fishermen between fishers and conservation managers. And, you know, this was because in many ways the fishers weren't behaving like the managers and the very expensive consultants thought they should, right? And, you know, in Jamaica, fishing is one of the few avenues where unskilled men can go out and make a livelihood and be their own boss. And in a post-slavery context like Jamaica, being your own boss was worth a lot more than just the income that a job provided. There was a lot of pride associated with it. And so people would make decisions that didn't make a lot of economic sense, and that would drive consultants and managers crazy because they would continue to fish beyond profitability and when better options presented themselves. But people often didn't want to go work in hotels and say yes to, you know, white tourists. That wasn't their dream. And so so this really got me involved in the complexities of coral reef conservation. As Bill mentioned, I went to go study at the University of Rhode Island. I worked with Richard Polnack, who's kind of the godfather of maritime anthropology. I then went on to do my PhD at James Cook University, where, as one of my colleagues put it, I became an ingrown hair. Stayed there for my PhD, all of my postdocs, became a full professor, and was eventually a center investigator and program leader for the ARC Center of Excellence for Coral Reef Studies. As Bill mentioned, I led a very intensive field-based program, primarily linking social science and ecology in Papua New Guinea, Kenya, Indonesia, Madagascar, Tanzania, Mozambique, Chile, Queensland, kind of all over the world, really. In January, I moved down to Sydney to launch the Thriving Oceans Research Hub. And what we're trying to do here is deliver solutions-oriented interdisciplinary research that increases the sustainability and resilience of our oceans and supports the people that depend on them. For me, thriving oceans isn't just about the ecosystems, it's about thriving ocean livelihoods as well and thriving coastal people. We're going to be really focusing very heavily on linking social science, fishery science, and ecology. And particularly for those of you guys who've worked in this field at all, those last two really don't speak to each other very well. And I'm hoping that as a social scientist, I can kind of play this bridging role between these disciplines that are very much at odds. And we're going to be doing work from both local to global scales. And one of the key things that we want to do is establish a global community of practice. We've started assembling our team. It's going to be a pretty big one. We've got a senior project officer, Thomas, who we've just hired. We're still working with an MPhil student, Adit, who's going to be based at JCU still. We've got a visiting student, Yi. I've got 2 research assistants, which I've hired. They're working remotely. We've got a database consultant, Ian. Some of you guys will be very familiar with Ian. He was my postdoc for many years before as well. He's moved back to the States at Princeton, and so he's working with me 2 days a week still. We're going to have 4 or 5 PhD students. We've just put our first offer out to Natalie, who's going to be joining us in a few months. And then I've just put out 7 postdoc offers, and I've gotten 6 yeses and 1, I'll tell you, on Monday so far. So we're looking at having basically an army of absolutely crazy good postdocs who work on statistics and data science, quantitative social science, social ecological systems, and marine ecology. So today's talk, kind of want to talk about, there's going to be kind of two main pillars of what my group does and what my what the talk will be as well. And the first is kind of this main event, right? It's the big thing that I got funded for, which is to identify the most resilient reefs and learn lessons from them about building resilience in other locations. This is kind of like a Hail Mary pass that we're trying to do. And so this is like, it's a 5-year project, and we probably won't know the answer until like year 5, day like 360 or something. You know, it's going to take a long time to put everything together. So in the meantime, we've got a lot of side hustles that we're doing, which kind of keep us in business, and we're really focused on answering some really fundamental questions about sustainability and conservation and coastal livelihoods. So let's start with the kind of main event first. As scientists, we're often trained, and we often spend our careers looking for averages and trends. And this can be really important for discerning the signal from the noise, which is why we do it. But we often, in doing so, we often ignore the most interesting bits, right? And so what I'm going to talk about are these interesting bits that we often dismiss, the outliers, right? Now, by their very nature, right, outliers deviate from our expectations, right? They're the things that are sticking out, they're doing things differently. And so consequently, they can provide novel insights into confronting complex problems where conventional solutions have failed. So there's a whole study of this called positive deviance analysis, where they're looking for outliers. And this has been used in fields such as business and health and human development to uncover local actions and governance solutions that work in the context of widespread failure. So in medicine, an approach has been developed to systematically study extremely resilient patients. These are referred to as exceptional responders. Now, they may, for example, have a remarkable response to drug therapy. You know, they may have, in a cancer trial or treatment, they may make a full recovery when most of the other patients don't. And this study of resilient outliers has led to major medical breakthroughs. For example, the treatment of HIV/AIDS was radically transformed after genomic sequencing of an exceptional responder identified a mutation that prevented the virus from infiltrating the patient's white blood cells despite repeated exposure. Now, this led to the development of a novel drug that mimicked this mutation, which radically transformed how HIV/AIDS was treated. Now, the exceptional responder approach is now a major focal point for oncology, and there's projects in Australia, Europe, and North America. Now, my laureate project will apply this exceptional responder approach to uncover the conditions under which some coral reef fisheries display unusual resilience. And then we'll try to learn what are the enabling conditions, and can they provide lessons for positive change in other locations. Now, this is effectively a kind of version 2.0 of what I kind of think of as the proof of concept for this. And that was a paper we did in 2016, and we got the cover feature in Nature for this, where we identified reefs that had more fish biomass than expected, given the conditions they were exposed to. Now, I want to be really clear, because a lot of people didn't understand this. These were not the reefs with the most fish, right? These were the reefs that were effectively punching above their weight. These were the reefs that had more fish than expected, given the maybe level of corruption in the country they were in, the level of wealth, the human impact that was there. And so we looked at a whole range of conditions, created a predictive model, and we looked for the outliers in that predictive model. Now, with time, I will say, and some follow-up studies that we did in one particular bright spot, we realized the real importance of not using a snapshot like we did before. I mean, I think it was really informative as a proof of concept, but what we uncovered in doing some follow-up work in one particular bright spot was that there was a real dynamic nature to that. And even though this place was bright, it was kind of dimming over time. So I thought there was a need to kind of move this forward in a way that accounted for the kind of dynamic nature of things. And so I was able to kind of leverage the success of this bright spots work after publishing it, a number of scientists kind of talked to me immediately afterwards, and in the year or two afterwards, saying that they were very inspired by this, but they had data from here, and or they were a colleague that was part of it, and they had new data from these 10 other locations. We ended up with about 10 times more data, about 26,000 sites, and we've got about 1,000 of them entered so far. So we're working on really throwing a lot more data at this problem to be able to look at it dynamically. So the first step for us is to locate the most resilient reefs. Now, to do this, I'll explore how key social, ecological, and environmental drivers are related to key metrics of fisheries resilience. Now, then we'll develop a predictive model to generate the expected trend as a counterfactual. And places that deviate positively from this counterfactual will be our exceptional responders. Places that deviate negatively, right, that are doing much worse than the counterfactual, these will be considered our poor responders. And then we'll look for places as well that are tracking along where we would predict, and we will call this our average responders. That's kind of our control group. Now, one of the things that I proposed was starting with the 2016 global marine heat wave as a focal event. But as I'm sure you guys in Cairns are acutely aware, there's been another global mass bleaching event. And so we may have to rethink what we use as a focal event for this. We may still use the 2016, but we may choose a different kind of focal event for it. So the next step is to use targeted field work to uncover the enabling conditions and explore how these could inform positive change in other locations. So in medicine, they systematically identify unusual genome, transcriptome, and metabolome features among exceptional responders. So what I'm going to do is I'm going to explore kind of social ecological analogs of each of these, right? So the genome is essentially the blueprint or code for doing things. As a genome analog, I'll examine key aspects of the social ecological context that enable or inhibits resilience, right? The transcriptome captures the processes that lead to the expression of the traits coded in the genome. And as an analog of that, I will examine key social ecological processes that convert the context into resilience. Now, the metabolome is the set of molecules that participate in the metabolic reactions, which is analogous to the elements that come into play to enable resilience, essentially the adaptive capacity, right? So we'll be looking at each of these dimensions in our field work. We're going to conduct targeted field work, send in a team to look at 5 exceptional responders, 5 average responders, and 5 poor responders. We'll conduct analyses to explore whether there's common enabling conditions, and if so, if these are going to be scalable, right? Are these applicable to other locations? Now, not everything necessarily needs to be scalable or applicable more widely. It may be that some of them are very contextual. So in this particular context, we can see it. Well, that's fine. You just go look for the places that have that context. And there's a medical analog for this too, right? Sometimes certain medicines work when somebody has a mutation. Well, if 8% of that mutation, of the population has that mutation, well, you know, you've solved this type of cancer for 8% of the population. That's a win too, right? So it doesn't need to, not everything needs to be totally scalable to the globe, right? There's other ways of thinking about it. Now, as I mentioned, that was our kind of, that's our main event. We're also going to be doing some side hustles. And I want to kind of take you through sort of 3 vignettes and these include what marine conservation has actually achieved, what is sustainable, and then I'm going to scare you with a ghost story. So one of the challenges, what has marine conservation actually achieved? We have no idea. In fact, I would say that we're completely even measuring the wrong things. We have no way of even finding out. We often use inputs, right? Things like the area conserved, rather than measure the outcomes. Now, this is just asinine because the outcomes are completely variable, right? You can get variability because people don't comply with the rules, right? And so you can have a protected area, and if nobody complies with it, it doesn't achieve anything. You can also get variability in outcomes because the ecological conditions in a certain place may or may not be conducive to rebuilding ecosystems, right? So there's a lot of social and ecological environmental reasons why there's a lot of variability. Now, in conservation science, there has been a move towards impact analysis. But there's practical and ethical considerations that often limit the successful use of kind of the gold standard, right? The gold standard is randomized controlled trials, right? And there's moral reasons not to necessarily do those because, for example, you can't necessarily just impose very strict conservation measures on very vulnerable people that are struggling to feed their children just to see what happens, right? That's morally repugnant, right? Sometimes people have been using things like natural experiments, which I would call kind of the poor cousins. Now, this is used in economics all the time. You may see that a policy gets rolled out in different states at different times, and so you can actually determine some causality, some attribution, because there's this rolling control. That's kind of a natural experiment. Well, what I'm going to propose today is what I would call the poor cousin of the poor cousin, right? This is the poor cousin. And this is a data-hungry kind of modeled counterfactual approach to estimate what would likely have happened in the absence of conservation. Now, this is a paper that's in the final stages of review in PNAS. In fact, we just have to submit one equation and there's no more review for it. So we're just on the cusp. And so this is led by Ian Caldwell. And so the first thing to note is we took about 2,500 coral reef sites globally. Now, there's a couple of things I want you to note about this map. And the first is that the size indicates the amount of fish that are there. And this again is in kilograms per hectare. So it's the weight of fish per unit area. And so the bubble is scaled by size. So you can see the bigger bubbles have more fish. We've also color coded them, and those color codes are based on the type of management that's at play. Now, this is going to come up over and over again, so I want to just go over the different types of management with you guys, right? So the gold ones are open to fishing, right? This means that you can basically go fishing, as you want. There's very few restrictions on the types of gears or the efforts that the amount of effort that is in play. The green ones are restricted fishing. These are areas where there are effective fishing restrictions in place. This might include, for example, a ban on certain types of gear. Maybe spear fishing is banned or gill nets are banned, right? We've then got no-take marine protected areas. These are areas that are that you're not allowed to go fishing in. And we've separated those out into 3 different categories, which are important. And the first, where the majority of them lie, are these are ones that are poorly complied with. Now, we used expert opinion. These are people that have been collecting data and often living nearby and working in these places for many years to gauge whether there's a lot of compliance, whether most people comply most of the time, or whether there's low compliance there. And so the majority of our reefs in this were these low compliance protected areas. For the high compliance ones, we separated them out into 2 different groups, right? And the first was what we would kind of consider the gold standard. These are the big and old high compliance marine protected areas. So big, meaning that it's greater than 10 square kilometers, and old, meaning that it's more than 10 years old. And we kind of use this as a rule of thumb. 10 square kilometers has come out in some studies of fish mobility. 10 is big enough where that many of the coral reef fish species that would encompass their range. 10 years old is because we've seen a lot of studies about recovery in marine reserves. In 10 years, you start to see quite substantial recovery by then. It's not fully recovered, but you can start to see some recovery then. Now, what we then did is we created a predictive model to predict the amount of fish biomass, right? And so there's kind of 3 things that I want you guys to take away from this thing there. And the first is something that's a seed that I'm going to plant later, because I'm going to come back to it. But one of the strongest predictors, negative predictors of reef fish biomass was our metric of what we call gravity. Now, gravity is a concept that's been used by economic geographers since the 1880s, and it's often been used to predict trade and migration flows between cities and between countries, and it's often been considered the most successful model in economics, right? Now, what we did is we basically calculated, well, the way it's often done is you take the population divided by the distance squared, and this is analogous to Newtonian gravity, right, which is mass divided by distance squared. We made a little tweak on this, right, because we did the population of a market and the population of a near settlement. But rather than distance squared as the crow flies, we use data layers of land cover and road networks to kind of, we did it in 2013, so it was like before Google Maps was really a thing, but we kind of created this least cost path between the city and the reef. And it was kind of like a Google Maps, right? So we created this travel time based on the least cost algorithm to create that. So we could divide the population divided by the travel time to get there. As I mentioned, we're going to plant that seed, and I'm going to circle back to that a little bit later. Now, one of the things we were able to do is control for a lot of human decisions, right? So things like what method people used. We were able to model the effect of different methods and then control for that. With the depth at which people surveyed, that has an impact on it. We were able to control for that. So the biomass that you see in that map above is effectively the marginal biomass, right? This is the biomass after removing these effects, right? We put it in the kind of most common category or at the global average for other ones. Now, what this also enabled us to do is because we knew the effects of management, we were then able to simulate what would happen if there were different types of management in place. Now, this isn't totally straightforward because, as you know, there's actually, as you notice, there's actually interaction, a significant interaction there. So it's not just a straightforward thing. Now, all right, so let's get to the main question. What does marine conservation actually achieve? Now, the key thing to note here is that there is a distribution. So first, I'm just going to present the data from sites that are open to fishing, right? And there's a distribution of biomass and sites that are open to fishing, right? There's not just one value. Right. So some sites have actually quite a lot of fish biomass. 1,000 kilograms per hectare is a lot of fish. Some sites have virtually none. Right. And so what we can do is we can actually plot those from the most biomass to the least biomass. And you get what's called the cumulative frequency curve, right? So you plot it from the most to the least. And so the initial ones have the highest contribution, and then the later ones have lower contributions, smaller contributions after that. We can do the same thing for restricted fishing, right? And so what you can see on the y-axis is the total amount of biomass is increasing on this. We can do the same for low compliance marine protected areas. Again, these don't contribute very much. And then we can do a lot for these high compliance marine protected areas, right? We can see quite a big bump there, right? So all of these together, right, that adds up to 100%, because that's our status quo. That's what we have in the ocean now, right? And this is just separated by the biomass contributions of different types of management. Well, what we were able to do is for each particular site, we were able to estimate what we think would have been there based on the model predictions if there was no management at all. Right. So we did this extreme scenario where everything was openly fished, but it was done for each particular site, given the social and environmental and ecological conditions there. We were then able to estimate what would likely have been if it was openly fished. And so what we call the difference, right, in the cumulative fish biomass between this extreme scenario where everything is openly fished and the status quo, this is the total realized gains. And this would equate to about 20% of fish biomass on coral reefs. Now, I can see everyone there. Did anyone guess about 20%? Anyone, you can raise your hand on the Zoom thing if you did. Anyone kind of guess around there? That was probably about where I would have guessed. I think I didn't actually do this. I probably should have. I think that was probably my gut feeling was it was going to be about 20%, but it's actually not right. And that's because we had to correct for a sampling bias. About a quarter of our sites were in fully protected marine protected areas, right? And this, the global actual amount is about 3%. So what this means is the people that provided us with data oversampled in protected areas. This may be because there's more funding opportunities or because there's more fish and it's prettier in protected areas, right? So in order to account for that sampling bias, we randomly subsampled from these marine protected area sites to recalculate a globally representative estimate. And what we came up with was about 10%, or in other words, about 1 out of every 10 kilograms of fish on reefs is from conservation or management. Now, I think depending on your orientation, your conservation orientation, this might be devastating news or it might be surprisingly good, right? I mean, I think, maybe if you spent your whole life working on marine conservation, you might say if we only got 10% a bump from all of the work that everyone's done, or you might work in some places and realize that that's actually a lot better than you expected because many places aren't actually doing very much at all. So I'll leave it to you to decide whether that's a lot or a little. I don't really have an opinion on that. But that's kind of what we got. Now, we had to do a couple of sensitivity tests in order to convince ourselves that this was reasonable. And one of them had to do with accounting for what's known as spillover. Now, spillover happens when fish inside a protected area swim outside, right? You get a density-dependent interaction where there's a lot of fish in a protected area. There's competition, so fish will swim outside, increasing the population of fish outside. Now, what that would mean for us, right? Our estimates rely on an accurate difference between protected areas and unprotected areas. And so what would happen if there was more fish outside of protected areas, the difference between fish and protected areas would diminish, and we would be underestimating the effectiveness of conservation. Now, conversely, the opposite thing can happen, and this is what's called displacement, right? So often when a marine protected area gets declared, right, let's just say 30% of the area gets protected, they don't take 30% of the fishers away, they push them out into the remaining area. So 70% of the fishing grounds get 100% of the effort, leading to overfishing in those areas and a greater difference between protected and unprotected areas. Displacement would overestimate our impacts of conservation. So what we did to account for this is we looked at the residuals, and we looked at whether our residuals changed with distance to marine reserves, and they didn't. We didn't see this. Now, I just want to be really clear because one of the reviewers latched onto this, and he's a lifelong kind of enemy of protected areas, and latched onto this and thought we should make a whole paper about this because he thought that we were saying, and I say he because I actually knew who it was who signed it. So he thought we should make the whole paper about this, about there not being spillover. And what we had to rebut was actually what we're not saying that there's no spillover. We're saying that it's not biasing our estimates, right? It could be that there's spillover and it's being captured. It could be that spillover and displacement are balancing each other out. We don't have a causal mechanism for why we're seeing this. And so it looks like we got away with not making this paper about there not being spillover. Now, understanding what's been achieved by existing coral reef protection efforts also requires benchmarking the status quo against the potential for further gains, right? Like maybe you've done everything that you could actually do and there's no more room for growth, or maybe you're a long way from there. So I'm going to bend your brain for a second just to illustrate that. And so what I've got in the kind of top right is the figure that you've already seen, and I'm just going to illustrate it a little bit differently. So follow through. So this was the status quo. That red line there is now, that's the status quo. And I want to now present the status quo as 0, right? So 0, we're just kind of going along the 0 axis there, right? The x-axis is 0. Now, the other one, that other line in black is the counterfactual, the model counterfactual if everywhere was fished. Well, what we did is we actually created an alternative counterfactual situation, right? Which we call the potential gains. And what we did is we compared the status quo fish biomass with the second full protection scenario, where all of the reefs are in big and old, high compliance, fully protected marine protected areas. Now, I want to be really clear here for a second. This extreme scenario is not intended as a policy goal, right? Prohibiting fishing on 100% of coral reefs would be economically, culturally, and nutritionally devastating for coastal societies. So we're not saying that this is where we should be going. But what we are doing is trying to understand what are the limits? What could, where is the scope? What could actually happen? What it allows us to do is gauge the status along a gradient from no fishing to fully fished to kind of see where is the status quo. Well, what it also does is it helps us identify sites that would benefit the most from protection. So the way we did that, again, the kind of purple blue line there is by stacking the sites from the sites that would have the highest potential gains to those that would have the lowest. And that's why you get that curve. And we've contrasted that with a randomized haphazard growth, where you just kind of, if you randomly put the points together, the sites in order, you would just get a linear growth line because you wouldn't have the first ones contributing the most. Now, what this allows us to do is calculate the difference in fish biomass that we would get by strategically selecting sites versus haphazardly selecting sites, right? And what we see is by strategically selecting sites, we would get, if we did a scenario of 30% unfished, which is basically what's happened with the Great Barrier Reef Marine Park, and what many other countries are aiming for as a target is 30% of no fishing zones. What we see given that scenario would be a 50% more fish biomass gains compared to haphazard selection. Now, so those sites that kind of fall under there are those that would give you the best bang for your buck, right? These are the sites that would give you the greatest potential gains, the greatest fish biomass gains when you protect them. Now, one of the so these include sites that had lower market gravity, lower chlorophyll, and lower sea surface temperature skewness. Now, one of the things that is hard to see, if you that line that's on the x-axis there contains a whole bunch of different points with different colors, and they're overlapping, which is a little bit unfortunate because you can't see that there's a great number of sites there that are actually in low compliance protected areas. They're already protected, just not effectively, right? So what we're getting at in this paper is some of the best conservation gains can be made not from declaring new protected areas, which is the incentives created by initiatives like the 30 by 30, which is about creating great tallies of how much is protected. But actually, we can make better conservation gains in many cases by improving compliance in existing reserves. Now, I told you guys in the beginning that I was a social scientist, and so far I haven't presented much social science. So I want to delve into some really quickly. And this is work that's being led by one of my PhD students, Stuart. And what Stuart's doing is a really cool experimental economic game, right? Where he's playing with real fishers in Townsville and getting them to play fishing games. Now, they're not just games because real money is on the line. They can win up to $50 for like 15 or 20 minutes of their time. So there literally is skin on the game for not just skin. They've got skin in the game for playing the game correctly, right? If you make good decisions in the game, you can actually walk out with a reasonable amount of money. So fishers in the game can make two decisions, right? They can decide to fish in areas that are open to fishing or in areas that are closed to fishing, right? And so the areas that are open to fishing have lower payoffs. Areas that are open to fishing have higher payoffs in terms of they catch more fish, but there's a probability that their stuff will get confiscated. Now, one of the fun things about what we're doing in this game is that we are actually looking at the role of social norms. So we're looking at what's the influence of what other people do. Now, this is what social scientists call the descriptive norm. Now, what we're able to do is create these confederate players. These are players that aren't really players, but appear on their screen. And these players, we can get them to, say, fish in the open areas. We can get them to fish in the closed areas. And the coolest thing is what we call a dynamic norm. So throughout the game, we can mix it up too. But the coolest thing is this dynamic norm where throughout the game, we can have more and more people, let's say, fish in the closed protected area, or we can do vice versa, right? We can go from closed areas to open areas. So this allows us to control and randomize what other people in the game are, or what other players in the game are doing to look at the role of norms. And the coolest thing that we're finding, preliminary data, is that this dynamic norm seems to have the biggest influence on players' compliance. So I think the big question really is kind of, so what? What does 10% more fish biomass mean? Does it mean things are more sustainable? Well, look, there's a lot of data out there, but we actually lacked reference points to even know what these assessments mean. And one of the big problems is that reef fisheries are extremely multi-species, right? Like I've done studies in Papua New Guinea where there's 169 different species caught by spear guns alone. And then, there's hundreds of species also caught by lines, by gill nets, and there are a different suite of species for each of these. So reef fisheries are literally targeting hundreds and hundreds of species. Now, fisheries models, right, multi-species fisheries models tend to have about 2 or 3 species in them. So they just will completely melt down if you put hundreds and hundreds. And we don't even know the relationships between the species to make these kind of multi-species, conventional multi-species fisheries models work. So what we've done is we've kind of treated all of the fisheries like a single stock, all of the species like a single stock. And this is a paper I was part of in 2015. It was led by Aaron McNeil. And what he was able to do is estimate the R, that's the recovery rate, right? He was able to estimate R from recovery over time in marine protected areas. Now, and what you see is it asymptotes. That's the figure on the left. It asymptotes. The problem with an asymptote is it can go on basically for infinity. So how do you know where to stop it? Well, what Aaron thought about doing was using data from really remote areas to anchor it. So we anchored it with sites that are 10, 20 hours away from humans that are rarely, if ever fished. And so what we were able to do is develop the first ever reference point for coral reef fisheries, right? We were able to say that the amount of fish we would expect on a coral reef without fishing was about 1,000 kilograms per hectare. Now, this was super cool scientifically, but I think it had low uptake because we used a global average. And you might say that coral reef fishers or coral reef managers are maybe a lot like parents, right? Like nobody wants an average kid, right? There's what we call the Lake Wobegon effect, right? Everyone's kid's better than average, right? They want the reef to be better than average too. And so I think it had low uptake because it was relying on a global benchmark. Well, my superstar, former PhD student, Jessica, really cracked the code on this. She did an absolutely amazing job. She's now doing a postdoc at Harvard. She was able to estimate site-specific reference points using a range of social and environmental conditions. And I've just listed some of the kind of environmental conditions here as well. Now, this allows us to develop reference points for each location based on their local conditions. And it's important because it was about 2 orders of magnitude difference between the lowest and the highest in these. So that's pretty cool. The challenge I have with what we've done in this so far is that we only used about 100 protected areas to estimate that recovery curve. And so our data was pretty sparse for developing a model like this. And what that meant was when we were selecting the better aggregate biomass dynamic models, right? So fishery scientists use several different competing models for these. When we were choosing between them, our model chose the best one, but the difference between that one and the next best one wasn't enormous, right? And there's massive sustainability implications between the competing biomass dynamic models, right? So let me give you an example of the most conservative model estimates the biomass at which the fish stocks are overfished is about 70 tons per kilometer squared. So when fish stocks are above that level, it's considered sustainable. That's the median value. And when they're below that, it's overfished. Well, our model selection chose the least conservative model, right? And so what that meant was we were kind of estimating what was sustainable at about half of the most conservative model, right? So I feel like we've done an amazing job. It's perhaps not quite ready yet for policy rollout because there's a lot of sustainability implications with choosing one of these models versus another. And in my view, one was better, but it wasn't so much better that I would risk a country or a location fishing down their biomass by half to say it's sustainable, right? So what we're now going to do is throw just a lot more data at it. As I mentioned before, we've got like 10 times more data, 26,000 sites from 68 different tropical countries. We're partnering with teams like the Wildlife Conservation Society, World Fish, state fisheries management and conservation organizations, and the United Nations Food and Agriculture Organization. And one of the cool things that we want to do is develop a decision support tool to allow people to provide real-time status and trends, to create downscaled analyses that are relevant at the scale at which decision makers are making decisions, and also to inform how managers could achieve key goals in specific contexts, right? So we can look at the trade-offs. What is the ecological trade-off if you choose, let's say, banning spear guns versus banning nets versus a fully protected place where fishing is prohibited? Okay, so there's just a couple of minutes here left. I'm gonna spook you guys with a ghost story, and this is the paper that Bill mentioned earlier that Jaden led in Nature just a couple of weeks ago. It was a really cool collaboration. I was so excited that they invited me to be part of it. And the reason I'm really bringing it up, not just to say thanks, but it's actually got really big implications for what I'm doing. So it's kind of opened up a can of worms for me. And not because I care that much about forests, to be honest, but it actually has some big implications for the way that I'm doing things. And so what Jaden and the others did was they traced satellite images, like thousands and thousands of satellite images, to actually uncover where the actual roads are, right? And this made a big difference when we compared the extent of roads that they got by tracing these satellite images compared to roads in the two major global road databases. We found that there was between 3 and 6.6 times more roads in our data that aren't reflected in this. And this is what's often being used in human impact conservation metrics in many times government policy and decision making. So we had 3 key results from this paper for me. And the first was that road density is the strongest predictor of forest loss. And so what we can see here is these are the variable betas, and road density is the strongest. We created alternative models where we use, this is with our data set, with the roads included, the satellite roads included. When we compared the same model, the same structured model, but using different data sets. So this is with the GRIP data set. And what I'm showing you here is the difference, the delta in betas, right? The delta in slopes in these. And we can see that the slope of roads is a lot smaller there. It's lower. And likewise, when we use the other data set, it's a lot lower. Now, the second key result is that there's actually far fewer roads in protected areas. And this is, there's about half of them. And this is actually after accounting for the fact that protected areas are often placed in in swamps or on mountainsides, which aren't suitable for agriculture and probably aren't going to have roads anyway. Well, we did a site matching study where we basically matched protected area sites with outside protected area sites with similar conditions, similar slopes and swamps or whatever. And so we found that there was far fewer roads. One of the things that was really interesting to me was that once the difference in roads was accounted for, protected areas had very little additional benefit to forest loss. Now, I will say that that is a unidimensional way to measure success in protected areas, and I don't think that's the end-all be-all. I think it's one important metric, but protected areas can do a lot. They can provide economic benefits, they can provide livelihood benefits, and a lot of other, so protected area benefits is a multi-dimensional concept, and we're only looking at one dimension here, and I think that needs to be emphasized. But for forest loss, once these roads were accounted for, protected areas had very little difference. Protected areas had very little additional benefits, which means that the main function that they're playing is to keep roads out. Now, to tie it all back, I think this has big implications for the gravity work that I'm doing. Now, what Jaden did was he recalculated the human footprint index. Now, this is one of the main global indices of human impacts on terrestrial ecosystems. And he recalculated it on the left using the conventional system with I think OSM data, might be GRIP, but one of the two leading databases, road databases. And then on the right, you can contrast that with what the human impact looks like when you use the actual roads. And it's much, much higher. So there's all of this unaccounted for human impact that's happening from roads. And I think that's really important, particularly for my work, where I'm actually looking at gravity, right? And my metric of gravity relies on these roads. So I think we need to really think through in my team how we're going to be calculating gravity and whether we can do something like use AI to scroll through satellite images and map all the roads in areas close to coral reefs. All right. Well, with that, I would just like to say thank you very much for listening to me blather on. It was really fun. Thanks.
Thank you, Josh. That was really good, really interesting. We end up with 33 people, which is not too bad. And particularly, as I said, we primarily terrestrial, so that's a pretty good outcome for a marine talk. Questions here or questions online? Feel free, anybody, to put your hand up virtually or really. Anybody here? Questions? Anybody online? Josh, I had a question for you about the gravity metric that you were using. So if I was understanding that correctly, I think it might be something we've played around with before, which is sort of like travel time to a particular locale. Is that right? So just regardless, yeah. And when you talked about that being really important, how close does a reef need to be to a population center, I guess you'd say? Is that a kind of question you can answer? Like at what point do you start seeing the effects lessening as you get further away?
Right. So, So the gravity metric is the population of that site divided by the distance squared. So we didn't just look at travel time. So it's an integrated metric, which is, population divided by distance squared. But I will give you two answers to that. And the first is that what we see is a bell-shaped relationship, right? So when you've got gravity on the x-axis and kind of the difference that protection makes, right? So we looked at the difference between protected and unprotected sites. In the most heavily impacted areas, the areas with the highest gravity, there's very little difference between protected areas and unprotected areas, right? If you can imagine, ecosystems are too far degraded for protection to make much of a difference, right? On the other side, what we see is that protected areas make very little difference in the most remote areas because there's very little impacts out there. So there's very little to protect from. And what we see is the maximum benefit you get from protected areas, the sort of sweet spot, if you will, is in medium gravity areas.
That's very interesting.
Yeah.
Any other questions?
Now, the second answer to your question, though, is one of the things that Jessica found is in looking at how remote did a place have to be before being more remote did not add any additional benefits. It was 20 hours away. So something 20 hours from a human habitation is what we would call remote enough where it's not being impacted.
Okay, we've got a online question, and I'll turn that over to that. I might come back to that metric, Josh, because that really is interesting. So online. Go ahead. There you go, Rochelle.
Hi, Rachel.
Thank you.
Yeah.
Hi, Josh. Thanks for the great talk. I really enjoyed hearing kind of similar projects to marine stuff that I've been working on, and it made me really curious about your relationship with conservation bodies, governmental and non-governmental, and is that relationship happening, or is it going to happen later, and or is there like a plan that's part of the project? Because from past experience, it's been very hard sometimes to get them involved with research that isn't directly, linked to them. Yeah. So I wondered what your experiences are with this, or the plans for your project, because this is very, important stuff for them.
Yeah, absolutely. So, so before I got my PhD, I got what I would call like the dream job, and it was with Wildlife Conservation Society. And I was the social scientist. I basically got a postdoc before I did my PhD. And I was traveling around Papua New Guinea and Indonesia working with a team of ecologists. I was the first social scientist that WCS had ever hired. And so I actually had been working with them since 2001. And I've got a super strong relationship. So they are very strong project partners on this. They're actually written in. We've got somebody on the steering committee from WCS. And so we are very, very tightly aligned. In fact, the whole data platform that we're using for our study is one that's been developed by WCS, and we're their largest partner in doing this. And so we're working very closely with that, with their data management team. I was kind of, as I mentioned, the first social scientist that they'd ever hired. My former PhD student, Georgina Gurney, she actually went on to work with them for quite a bit and has really helped them roll out their global socioeconomic monitoring of kind of protected areas. So we've got really strong relationships with kind of international global NGOs. We've got the UN FAO as a project partner, and we've got WorldFish, which is an intergovernmental organization, right? They are basically a development research organization based in Malaysia, part of the CGAIR. I don't know that acronym for that very well, but they're part of that group there as well. And so they're project partners on this as well. And so we've been linked with them. I've been working with them for many, many years. And so we've got some really great and long enduring partnerships, but we've also got some new ones, which is really exciting as well.
That's very promising. Sounds great. Thank you.
Okay, any other questions? Josh, I just want to come back quickly, if you don't mind, to that gravity metric. So that the way you set that up, so you've got, I guess, local population density divided by distance squared. Obviously, when you square anything, you're going to have a strong effect. So that's inherently built into that metric. But my understanding is you empirically tested that metric against your response variable, and that was the thing that jumped out as being the most important. So you have empirical support for that particular formula, as it were.
That's right. And so, so we've done this, we've used this a lot. And so in the course of the years at which we've been doing it, we've basically tested every combination, right? So we've tested, should it just be divided by the distance or the travel time? Should we do it divided by cube? Should we do it by the square root? Should we, we've tested all the permutations of it. Squared works great, which is the original formulation of it. I don't think that they probably tested all of those ones initially. Squared works great. right? So we've just been using that. We also tested different places in which we could start from, right? So what I presented to you was the distance, the gravity of the nearest market. Now that market is a port, a provincial capital, or kind of city of interest. There's not a global database of fish markets. I wish there was, I would use that. There isn't. So we use these kind of big, main kind of cities sort of things, ports, provincial capitals. And we also used the nearest human settlement. So it was any cell, regardless of the population, as long as it was not zero, right? So we looked at the nearest human settlement, basically. We calculated there's two different gravity metrics. But in our original formulation of it, we also thought that maybe peri-urban markets were the ones. So we did a kind of population density of 40 people per 40 people per kilometer, so it must have been more than that. 40 and 75, maybe it was, yeah, anyway. I can't remember exactly the population density, maybe it was per kilometer squared. But so we kind of looked at these different thresholds of population for a particular region or cell, and found that actually what worked best was our original intuition, which was the market and the population, the local near settlement.
Okay. All right. Well, that's very interesting. I like that. Any other questions? Okay, Josh. Well, thank you very much, mate. We really appreciate it. And thank you. I know you're super busy down there with lots of things. You actually look like, Josh, you look like you might have lost a couple kilos, just looking lean and mean at the moment. Probably really busy, I'll bet, huh?
Yeah. Well, I think it's actually because I quit drinking about 1.5 years ago. So right.
Well, great. Yeah. All right, Josh. Well, thanks very much, mate. All good luck. We hope we see you sooner rather than later. Okay.
Great.
Bye-bye.
Thanks, Bill. Bye, everyone.
Oops. All right. Food, beer. Okay.